Hi and welcome to this video. My name is Jan-Hendrik and in this video I would like to cover the topic measures of central tendency. Let's see what I planned for this video. The first thing I would like to introduce is the mean, or more precise, the arithmetic mean. Then I would like to show the median. Then I would like to go into minimum and maximum. Then I would like to introduce the quantiles. The quantiles are a, let's say, main headline for the quartiles and percentiles. Then I would like to introduce the mode. And last but not least, I would like to discuss when to use which method or which measure of central tendency. I'm going to do this twice because I want to show you, first of all, how to calculate all that in R, and later then we are discussing the math and the theory behind it. Let us first have a look what all that is for. So, on this slide you will see a typical output of a statistics program. Well, here it's in German. Nevertheless, you will find this in many languages and for many statistics programs with a typical descriptive statistics. Descriptive statistics describe the numbers or describe the metrics that you have in your data set. So you will see something like the arithmetic mean, median, minimum and maximum that we're going to discuss today, as well as the percentiles, and interquartile distance is just the distance between two quartiles, so you will need quartiles to understand what that is. The others here are measures of dispersion. But what does it all lead to? It leads to those beautiful tables that you will find in nearly all empirical journal articles, and it's typically always the same thing or the first thing that researchers show. They give an overview over their data, and what do we here see? We see that this researcher, whomever that is, has made a full sample and two subsamples, and here we see that he or she had 12,000 observations, and here we see the mean, here we see the minimum, and here we see the maximum. Some other researchers use more measures of central tendencies, other will show less, just like this one. Here I prepared some data for this video. I chose to use income data as an example because income is so widely discussed in the practice, in the public, in the press. So let's discuss some income. What is discussed about? Typically the per capita income, the per person income. And well, the per person income or per capita income can be defined as an arithmetic mean or as a median of the income of a certain population, of a country, for example. So here I prepared some data of a very small population of only 9 persons. We have one person with 22,000 euro income, one person with 24, 25, and so on and so forth. And the rich guy here to our right has an income of 105,000 euro.
Hi guys, I'm Richie.
We know who you are. What, no chopper?
We can display this in a so-called strip chart. And the strip chart has only one axis, the x-axis, or here the income axis. And here we see dots for each person. So 22, 24, 25, 30, 34, 50, 65, 70, and 105,000 euro income. We see that the distribution is not really, well, equally distributed. So we see something like a dense part here and a quite stretched part of points here. So there are only a few people with a high income and there are quite many with a low income, but this reflects more or less what we see everywhere in the world.
Yeah, might end up being true, you never know.
So let's make calculations in R, and I switch to RStudio and then I show you how it works out. Now I have arrived in RStudio, and the first thing I do, as always, is to open a new script window and to give a beautiful headline to my code. 1, 2, 3, 4, 5. Of course, we need the data, and the income that we just saw as a table would be a beautiful vector, of course. A vector income, and I assign with the C command, which is the combine command, all those numbers. Let's start with 22,000, then 24,000, 25,000, 30,000, 34, 50, 65, 70, 105. Okay. Now, if I run this line, we see that in our environment, this vector income appears with 1 to 9, so 9 elements. Okay, the first thing we wanted to discuss is the arithmetic mean. And the command for the arithmetic mean is the mean command, and we just hand over the vector income. And I run this line, and down here in the console we get the answer. It's 47,222 euro. That is the arithmetic mean calculated by R. The next thing is the median. The median is the middle value, the one that is exactly in the middle if you previously order all those data points. They are already ordered, as you see here. We start with the lowest and we end with the highest, and we have 9 of them. So the fifth is the one in the middle. That must be the median. Let's check that. And we use the median command, and again we hand over the vector income and run this line, and indeed the median is 34,000, which is the value in the middle. Now let's have a look if we can find out about the minimum and the maximum. Of course, we have the min command to do that. The vector income has to be handed over, and the minimum is 22,000. Let's check. There is the minimum value. The maximum, of course, will be, oops, not mac, but maximum. Let's run that one, 105,000. There it is. And let's check that. It's 105,000. Okay. Let's switch to our quantiles. So if you don't know what that is, I'm going to explain that later on. Only briefly, we talk about the quartiles. In the quartiles, the word quartiles comes from quarter. So we split our data into 4 quarters, the lowest one, 2 middle ones, and the upmost quartile. So 4 quarters, and the percentiles. And in fact, we only have a percentile command, but it's called quantile here. So quantile, of course, we have to hand over our data, and we have to hand over, and that is very interesting, the percentile here that we want to have, so the percentage. So we want to see, and I hand over not only one, I hand over several. Accordingly, I use a vector here. We want to see 0, the 5% percentile. That's the value where 5% are smaller and 95% are larger. We want to see the 0.25, so the 25% percentile, where 25% of the data is lower and 75% of the data is higher. This is in line with the definition of the first quartile, because quartiles, 25% is the lowest quartile. Let's see the 50% percentile, which is in line with the definition of the second quartile and which is the median. Then let's see the 75%, which is the third quartile. And let's see the 95% percentile. Why the 95% and the 5% here? Because they're often used, for example, in risk management and so on, because often values being the lowest 5% and values being the higher than the 95% percentile are meant to be outliers. And exactly that's the reason why to look at these values. Let's run this line and we get back a beautiful table here, a beautiful one. So the 5% percentile is calculated as 22,800. So only this one is lower than the 5% percentile here. Then we have the 25% percentile, or the first quartile. Then we have the 50% or second quartile, which is the median. It's exactly the value in the middle. Then the 75% and the 95% percentile. Beautiful. The last measure I would like to introduce is the mode. And the mode is the most observed value in your data. Since we don't have any of those data points that we have observed even twice, we need other data, maybe some nominal data here. So let's introduce a vector gender. And I would like to assign, of course, a vector to this with gender. So we have a boy here, and another boy, and another boy. Then we have a girl, another male person, another female person, another female person, another female, and another female. 1, 2, 3, 4, 5, 6, 7, 8, 9 fits perfectly. I run this and I have a vector gender with male, 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 female, male, female, female, and so on and so forth. Now, since there is no mode command available here, we can misuse the table command. So let's use the table command and let's hand over this vector gender. And I run this and I get the answer that there are 5 females and 4 male persons. Of course, we now want to take out of this table the highest value, which is the value for the females. 5 females and only 4 males. So what can we do? We can use the maximum command to this table command. So we take the maximum from this table, and of course we have to hand over the vector gender, and there is our mode. That's a little, let's say, retour or workaround to get the mode from nominal data here in R. If we now have a large data set, and not only male and female, but many different groups, we can also use the whichmax command to find out. And of course we have to hand over the table again with the data, and that command will tell us that the female is most often named. And what's the one here? The one is the column index. It's the first column in the table. Well, that's it for R. Now we switch back to PowerPoint and I show you a little theory around. Okay, so what did we do here? The arithmetic mean, most of you will know from school, is calculated as the sum of all observations divided by the number of observations. Now, if we want to have the arithmetic mean of the income, which is typically written as income with a line above. So everything with a straight line above is typically the arithmetic mean. We have to add all those numbers. 22 is here, 24 is here, 25 is here, and so on and so forth, and divide that by the number 1, 2, 3 to 9. So we have 9 observations, and that is 47,222, as we know from R. So exactly this number here, just abbreviated it and left away all those zeros. If we want to put that into a formula, we can use, well, a bit more advanced variables. So we have the arithmetic mean of the variable x that is given as x1, x2, x3, which are the observations. So x1 is 22,000, x2 is 24,000, x3 is 25,000. So x is not one variable, but it's 9 variables. They can be distinguished by their index, which counts from 1 to 9. N in statistics is always the number of observations. Since we have 9 observations, n would be 9. But for a very large data set, even this formula would be quite unhandy to use. So we use this mathematical formula here. We divide 1 by n, dividing by n, and we use the sum sign. How to read the sum sign again? The sum sign counts the indices. So the index I will be counted from 1 to n. N is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Accordingly, the xi here will be replaced by x1, x2, x3, and so on. And since it's a sum sign, it is x1 plus x2 plus x3, and so on, up to x9. Accordingly, this sum sign will do exactly the same that is written in one line here. I, the index I, counts from 1 to n, and we add all those x with the indices I. This is how we can read this. If we now show the arithmetic mean in our strip chart, we see that there is a certain number of observations left to it and a certain number of observations right to it. They must not be necessarily the same. So here we see 5 observations, here we see 4 observations. On the left-hand side, there are more dense, more close to each other. On the right-hand side, they are more stretched, more far away from each other. If we now remove the rich guy to the right-hand side and we replace this person by an even richer guy, like Richie Rich or whomsoever, so the person with 105,000 income leaves the room and someone with 1 million income comes into the room, what happens then? So from this calculation, I just removed the 105 and replaced it by 1,000, which is 1 million in this case. The arithmetic mean jumps up a lot, nearly 100,000 of income. So the arithmetic mean would now move far away. And if we look at this number, 146,000, even all other 8 observations, they would all be smaller than the arithmetic mean. Only the rich guy is right to the arithmetic mean. And indeed, this discussion is very, very important, because if there is only a few rich people in, let's say, a nation, the arithmetic mean of the income can be skewed or can be biased a lot by only a few persons here. If you assume this to be a statistical outlier, of course, the statistical outliers can distort your arithmetic mean. This cannot happen to the median. If we now look at our data again, the median is always the middle observation. Since we have 9 persons in our sample, the middle person is exactly the median, or represents the median. That's why 34,000 was exactly the median income here. What happens if we have an even number of observations? Then, just like in this picture, there is no median person, there is no middle observation. Then we take the person left to the non-existing middle and the person right to the non-existing middle. So the one with 30,000 and the one with 50,000, and we take the arithmetic mean of these 2 persons. The arithmetic mean? What about the outliers? No problem. Outliers would be here on the right-hand side and would be here down on the left-hand side, but they would not be here in the middle. So even a median calculated on the base of an even number of observation is still very robust to statistical outliers. If we want to write this in a mathematical form, we can calculate the median for an odd number n. For an odd number n, an odd number n has 2 halves plus 1 person. The left half and the right half. So 2 times m plus 1. M is the size of one of those halves without the person in the middle. And then, of course, x m plus 1. This is xm, because if we halve this, 4 is a half. This is the 4th person, and the 4th person plus 1 is the one in the middle. This is how it can be written. For an even n, of course, we can directly split it, and we can take the arithmetic mean of only 2 persons, the person m, this one, and the person m plus 1, it's this person, and we have the median. Now, writing this median into our strip chart, we see that the arithmetic mean and the median are not necessarily the same. Typically, or often they are the same if we have a symmetric distribution, a distribution that looks the same on the right-hand side as on the left-hand side. But income is not symmetrical distributed, so the median is a lot more left, since the rich persons here on the right-hand side pull the arithmetic mean to the right. The minimum and the maximum, of course, are self-explaining. It's the one with the least income and the one with the highest income. They are on the left and on the right-hand side. Not so self-explaining, of course, are the quantiles, the quartiles, and the percentiles. The quartiles split your data into 4 heaps. The lowest, 2 middle groups, and the highest, all of them being 25% of the data. And of course, the values that you have to split them are called quartiles, because they quarter your data. Accordingly, the first quartile is also called 25% percentile. That is the value whereof 25% are lower and 75% are higher. The median is the second quartile, or the 50% percentile. It splits the data into 50% being lower and 50% being higher. And the third quartile is the 75% percentile. It splits the data into those 75% being lower and those 25% being higher. Of course, if those percentiles or those quartiles do not exactly match with a certain observations, there are also methods how to calculate them as some kind of weighted mean between 2 persons being next to these, let's say, frontiers, cutoffs. The mode then is simply the most seen or most observed number in your data. It is better to understand for nominal or ordinal data. If we have more females than males, the female will be the mode here. For metric data, we need some density plot maybe, and the highest value of this density will be our mode. Nevertheless, that is some kind of, let's say, artificial. And accordingly, the mode is not often disclosed in articles in statistics. Now, when do we use which measure of central tendency? Of course, the mode can be calculated for metric data, but there are a lot of downsides, and I wouldn't do that. So it is theoretically possible, yes, but let's say better don't do it. But for ordinal and nominal data, of course, the mode is very, very important. The median can be calculated for metric and ordinal data. Since ordinal data is ordered, you will find someone in the middle. But you can't use it for nominal data, of course. And the arithmetic mean can only be used for metric data, but not for ordinal and not for nominal data. And that was it for today. Thank you for watching the video and see you in the next video.
Wow, Big Jim, David.
I thought it was one of these guys.
Little Ray Ray.
Alright,
Dirtbag motherfucker.
hey, for the hazard for today, we got these motherfucking nuts. Fuck you, you're cool, fuck you, you're cool, there's my fucking bag. Here's a good can of go fuck yourself, I'm out.
That's it.
You out of here, Curtis?
Go. Appreciate it.
That's pretty good. I like that one.
Short and sweet. Right to the point. See you next time.
All right.